Hello, in this video we're going to code with explicit differencing to simulate thermal profile of a bar. And so we're given that the length of the bar is 20 meters, the thermal diffusivity of the bar is 1 meter squared per second, the space increment is 1 meters, and the max time step is going to be 0.5 seconds. And so here we have the bar drawn with 20 increments because it's 20 meters, 1 meter long each increment. On the left is 50 degrees and on the right is 80 degrees. And so before we go in code, we're going to derive a few equations that we'll be using in the code. And so to start, we're going to start with the heat diffusion equation, which we derived in a previous video. And so before we touch the heat diffusion equation, we're going to start by discretizing the position and the increments as well as the time increments. So each of these increments we'll call delta x. And so if we were to count each increment and so forth, we can give the counter a variable. So if we were to call this j, and then we'll also, as time goes on, be having a change in time, and we can give each time increment. So we'll have 0.5 seconds, and then 1 second, 1.5 seconds. And so each of those we can give a counter as well, and we can label that as n. And so the reason we do this is because x, if we base it off the counter and the increment, x is going to be defined as the change in position, the change in the length, times the counter. And then the same with time. Time is just going to be the change in time increment times the counter of the time. So we'll have delta x times j equals x, and delta t times n equals t. So that's for position and time. And so if we start here, we're going to give the approximation for the change in temperature with respect to position. And so if we take the first derivative of the change in temperature with respect to position, we're basically going to have the temperature of this block minus the temperature of that block. So if we were to have, just to call this block J, this block would be J plus 1, this block would be J minus 1, and so let's just say we use these two blocks here. We would have the temperature at block J plus 1 minus the temperature at block J, these two blocks that are right next to each other, and then we have it divided by the change in the position. So this is the difference in temperature and the difference in position. And if we were to take the second derivative of that, so the second derivative of the temperature with respect to position, we would have the slope. So this here is the slope between these two blocks. So we would have the slope between these two blocks minus the slope between these two blocks all over the change of position. So we would have T, the temperature at the increment J plus 1 minus the temperature at the increment J divided by the change in position delta x minus the temperature at the increment counter J minus the temperature at J minus 1. So these two blocks and these two blocks all divided by the change in position, and this entire quantity divided by the change in position. So we have the approximation of the second derivative of temperature with respect to position is approximately the temperature at the increment J plus 1 minus 2 times the temperature at the increment J minus the temperature at J minus 1 divided by delta x squared. And then this would be actually a positive because minus, minus, a minus. And then moving on, we need to approximate the change in temperature with respect to time. And so that's going to be approximately a similar process. So you're going to have the temperature, instead of using J's now, we'll be using N because we're moving to a different counter. So we'll have the temperature at position N plus 1 minus the temperature at the counter N divided by the change in time. And so these temperatures we can actually, so these are all at the same time and these are all at the same position. So what we can do is label these all at the counter N, and these would all be at J. And then so we can actually have this be J plus 1. And then what we can do is we can set these equal to each other in the heat diffusion equation. So we would have the thermal diffusivity alpha divided by, we'll take out the delta X squared here. And then so that leaves us with the temperature at, so the numerator here, J plus 1, N minus 2, J N plus temperature at J minus 1, N is equal to this approximation on the right. So the temperature at J plus 1, N minus the temperature at J N. And then what we can do is we can divided by delta T. So we can multiply this over to the left side. So that would give us alpha times the change in temperature. And then we can isolate, excuse me, this is still J and then N plus 1. You can't just switch that around. And then so what we can do is we can move this over to the other side because these are equivalent. So we'll have a plus TJN here, but the difference is this TJN has this alpha times delta T over delta X squared, and so this quantity we can give a variable, so we'll set it as R. And so this does not have that. So when we're moving it to the other side, we have to make sure that we include that. So this would be 2R technically, and then this 2R TJN, and then this would just be 1 TJN. So when we're simplifying this, we have that the temperature at the increment J for position and the time N plus 1 increment is equal to, we'll have R T J plus 1N minus 1 minus 2R TJN this should be TJ plus 1N, and then plus R TJ minus 1N. And so that equation here is what we'll be using in our code. Now we can begin coding, but real quick, I made one mistake when I was writing out and deriving the equation. It was originally minus 1 minus 2R the quantity of that, that should be plus because I took the negative out. So I just forgot to switch a sign, but that's going to be important in just a minute. So first, when we begin our code, we're going to import numpy as np, and we're going to import from plotly dot subplots. We're going to import make underscore subplots. So the first pack allows us to use some mathematical functions, and then the second allows us to plot out our thermal profile. So the first thing that we're going to do is input all of our givens and our inputs. So we have that dx is equal to 1, dt is equal to 0.5. We have that the r value, which is the variable that we defined earlier, is equal to alpha, we'll call it a, times delta t, and that's going to be divided by dx squared. And so we have to define alpha, which is the thermal diffusivity, which we are given is 1. And then we have our temperature. So T, the temperature at the left is 50, temperature on the right is 80. And then something I forgot to mention earlier, the temperature of each increment is 20. So we'll call that T naught is equal to 20. And then we have 20 increments. And so if we shift enter, that is all of our givens. And then so we have to create an array for all of our temperatures. So we'll have the array is equal to np.array. And then so np.array is going to create an array. So we want the number of arrays and then the values in the array, which would be the 20s. But the thing is, we're going to use np.full, because what that's going to do is it's going to create an array for us, and each value in the array is going to be 20. So we see here, creates us an array, each value is 20, and then we want to define the first value. So Python indexing starts at 0, not at 1, so the first index is going to be the left, the value on the left, which should be 50, and then the last index, so for Python, indexing of the last value is -1, that's going to be the temperature on the right. And so if we print this out again, we can see that's 50, and then it's full of 20s, and then it ends with 80. And so what's going to happen is we need the temperatures to update. So the temperature, if we were just to look at the increments in between the initial on the 50 and the on the left the 50 and then on the right the 80, we would have it start at 1 and then go to the last value, which is -1. And the reason we do -1 is because if we were to print out, this is like we're taking a slice of it, if we were to print out from 1 to, let's say, 5, so you see that there's only 4 values because it doesn't take the last value. So when we do to -1, it's just going to be the 20s, it doesn't take the 80. And so we take this, those are the numbers we're going to be working with, and we need to update it. So each time the values are multiplied by that r variable that we mentioned earlier, that constant that we gave. So r times, and then when we derived that equation earlier, the first value is the temperature at the next increment at that same time, and so it would be r times the temperature and then the indexing would be 2 because it's the next value, and then it's all of them, and then plus, so we have that 1 minus 2r that we derived earlier, and then it's the same time increment as the 20s that we have here, so we'll just copy and paste, and then it's plus, and then we have r again times, and then it's the j minus 1, so this is going to be all of the previous values, so we'll do t negative 2, should be 2 times r. And then so if we have this here now, it's just going to print out one of them, so what we need to do is create a loop, and so for I in range, let's just start with 100, and then if we were to print the temperatures each time, we have all of the array values here, and so it prints it 100 times, and so now what we want to do is we want to plot it instead of printing it. So first we have to plot the initial values, so we're going to make the plot first, which is fig, we'll call it a figure, goes make underscore subplot, so this just initiates the subplot, and then fig dot add underscore scatter, so this is going to add each time, and so we have to have some x values, so we'll have x in range of basically the number of time increments there are, so x equals np dot arrange of n, so x is just going to equal n. So basically what that does is it makes a list of values from 1 to the range of the number that we gave, which was 20, which is the number of time increments. And so x is going to equal x, and then y is going to equal the temperature. So this is going to be the initial temperature array, and so the mode, it's going to draw a line, so, and then we'll name this one and then so it's going to do this every time. It's going to plot a new one, and this will now be the new like iteration. And so what we did with f and then the brackets is it's going to allow us to change that number into that integer into a string, and then we're going to have to update the layout because it's going to give us a lot of iterations. So in order to actually be able to see it, we need to make the graph big enough. So we'll update the width to 800 and the height to 600. So now it's plotting. As you can see, it is very messy and very crowded, and there is a lot of values, and it also has 2 zeros because it initiates it, so we'll go from 1 to 100. That way it will start at the next iteration, so now we only have 1 0, but it's still very messy and there's still a lot. So what we can actually do is add in an if statement, so it'll only plot, let's say, every 10 iterations. And so how we're going to do that is if we were to have, let's say, 30% sign 4, that gives us 2. And so what the percent sign does is it gives us the remainder. So obviously 28 divided by 4 is, 28 divided by 4 is 28 is the biggest multiple of 4 under 30, and so there's a remainder of 2. And so what we can do is use this remainder function to add in the if statement. So if it were to only plot every 10, so I, number of iterations, remainder I divided by 10, and the remainder is equal to 0, and then it would plot, it gives us a much neater graph. But as you can see, it's not quite reaching steady state, so that means we need to go a little longer. So let's say we go to 1,000, and we'll do every 50 equals 0. That gives us a nice, neat little graph that reaches steady state. So that's the thermal profile. Something of the bar, something that I do want to add on is if I were to change the time step to, let's say, 0.51, this would in turn change the alpha value, and what it actually does is it creates this wonky, funky graph. It's not exactly stable because the R value is not, there's a limit on there's a boundary on the R value, and so when we go past 0.5, say 0.501, it's still stable. If we go to 2, it's still stable. Let's say we went to 8, and then it destabilizes. And so anything less than, so if we were at 4, it still is stable, and there's not much wiggle to it if we went above. So as you can see, when we go past 0.5, that's when it starts to destabilize. And so in the next video, we'll actually show theoretically why this happens and what the boundary on R is. But this is the code using explicit differencing to simulate the thermal profile of a bar.